Why doesn't milk settle into layers like sand in water, even though neither one is a true solution? The answer is a whole hidden category of mixtures in between, and by the end of this video, you'll be able to tell a solution, a suspension, and a colloid apart just by looking at them. Every mixture is either homogeneous or heterogeneous. A homogeneous mixture or solution has uniform composition throughout. Stir sugar into water properly and every sip tastes equally sweet from the first to the last. A heterogeneous mixture does not mix uniformly. Sand and water or oil and water, you can still see the separate parts. In a solution, the solute is the substance being dissolved, and the solvent is the substance doing the dissolving. We express how much solute is present using concentration, mass by mass percentage, mass by volume percentage, or volume by volume percentage, depending on what's easiest to measure. For mass by mass percent, percentage equals mass of solute divided by mass of the total solution times 100. And that total solution mass includes both the solute and the solvent added together, not just the solvent. So if 10 grams of salt dissolves in 90 grams of water, the total solution is 10 plus 90 equals 100 grams, and the mass by mass percentage is 10 divided by 100 times 100, which is 10%. Once you know a mixture is homogeneous, you separate it using differences in physical properties. Crystallization separates a solid from a solution using solubility differences with temperature. Solid solubility generally increases as temperature rises. So if you cool a saturated solution, the solvent can no longer hold as much solute, and the excess crystallizes back out as pure solid. For example, if a saturated solution holds 287 grams of a compound per 100 grams of water at 60 degrees, and solubility drops to 241 grams at 40 degrees, then 287 minus 241 equals 46 grams, crystallizes out on cooling. Distillation separates liquids by their differing boiling points. You heat the mixture until the lower boiling liquid vaporizes first, then cool and condense that vapor back into pure liquid. Distillation works well when boiling points differ by at least 25 degrees Celsius. Acetone at 56 degrees versus water at 100 degrees is a good example. When boiling points are closer together, like in petroleum refining, fractional distillation handles the smaller differences instead. And paper chromatography separates mixture components based on how fast each one moves along wet paper. Components that cling less travel further, which is exactly how you separate different colored dyes in ink. Heterogeneous mixtures need different tools. Immiscible liquids, ones that don't mix at all, like oil and water, are separated using a separating funnel. The denser liquid settles at the bottom and is drained off first through the stopcock, leaving the lighter liquid behind. Sublimation separates a solid that vaporizes directly, solid straight to vapor with no liquid stage in between, from one that doesn't. Heat a mixture of camphor and sand gently, and the camphor sublimes away as vapor while the sand is left behind, since sand doesn't sublime at all. Don't confuse sublimation with evaporation. Evaporation is liquid turning to vapor. Sublimation skips the liquid stage completely. Centrifugation spins a mixture rapidly so heavier particles move outward and settle. This is how blood components get separated in a lab. And coagulation uses a coagulant, a substance that makes fine suspended particles clump together into larger masses that settle out. Alum does exactly this in muddy water, turning fine suspended dirt into settleable clumps. Now here's what ties it all together. Particle size. Solutions have the smallest particles, too small to scatter light, and they never settle. Suspensions have the largest particles, over 1,000 nanometers, big enough to see, and they settle out over time if left undisturbed. Colloids sit in between, with particles from 1 to 1,000 nanometers, too small to settle like a suspension, but big enough to scatter light, which is called the Tyndall effect. A true solution, like salt water, does not show the Tyndall effect. But milk, blood, and fog are all colloids. They don't settle like a suspension would, yet they do scatter light unlike a true solution. So if you shine a laser through a mixture and see a visible glowing beam path, that alone tells you it can't be a true solution. It's a colloid or a suspension because a real solution's particles are far too small to scatter that light at all. Quick check, the question's on screen. Pause if you like, but try it first. 10 seconds, go. A laser beam passed through a jar of liquid shows a clearly visible glowing path through it. Is this liquid a true solution or a colloid? A visible beam path means light is being scattered, and true solutions never show that. Only colloids and suspensions do. So this has to be a colloid. Homogeneous mixtures are uniform and get separated by crystallization, distillation, or chromatography. Heterogeneous mixtures aren't uniform and get separated using a separating funnel, sublimation, centrifugation, or coagulation. And particle size is what separates solutions, suspensions, and colloids, with the Tyndall effect as your quickest test. Free notes in the description. Subscribe to Clarix for the rest of Class 9 Chemistry.